So what we can do now, now that we have the trig derivative shortcuts, we can start to find derivatives or equations of tangent lines for functions that involve trig in some capacity. So on the next page, we're going to take a look at a few examples, some with trig, some without, but nonetheless, they're all going to be good reviews. So we're going to find the equation of a tangent line to the graph, specifically at the given point. And let's see, for the first one, notice how this is not in a polynomial type form. We want to expand it to get rid of the parentheses and make sure we just have x's to some powers so we can easily use our power rule shortcut. So before we take the derivative, I'm just going to go ahead and rewrite f of x, the original function. And it might take some time, but for the first part here, if we square it, we can go through a FOIL process. We'll get x squared plus 2x plus 1. And then you'd have to take the time to take that quantity times the 2x minus 1 that you still have left out front. Now, through movie magic, if you were to go through and do all of that and then combine some like terms, we'd have 2x cubed plus 3x squared minus 1. So this is technically how the original function would look like in standard form or kind of polynomial form. So from here, we should be able to take the derivative, and that's when we're going to use our f prime notation, and we'll go ahead and apply our power rule. So power rule on the first term would change to 6x squared. Power rule on the second term would just be a 6x, and the derivative of a constant is 0. So here's our derivative. We can go ahead and use that to our advantage to find our slope to help us write the equation of a tangent line. So we specifically want the tangent line equation at -1. So if we were to plug in -1 for those x's, we would have 6 minus 6, which would be 0. Now, before we go on to the point, this might be something worth noting here. Notice how the derivative is 0 at this x location. So if our derivative is 0, that is a potential, okay, max or min. If we have that flat or horizontal tangent line, okay, has that slope of 0, we have a potential max or min on the graph at this spot. Let's go ahead and try to find the point though. So this is where we'll plug -1 into the original equation. Now you can plug it in at the very top, you can plug it in into your expanded form. It doesn't matter which one because it should give you the same result in the end. So this would be -2 plus 3 minus 1. And that would be 0 as well. So point slope form, if you prefer that one, remember it's going to be your best friend this year. Your equation of the tangent line would look something like that. If we take a look at the next one, notice how we do have some trig. Now, notice how if we are using trig, we're most likely going to have the variable theta in some cases. But if you would prefer working with x's, you can simply write x in the spot and it's going to work the same way. So let's go ahead and try to find our derivative. Now the derivative of sine is cosine, according to what we saw on the previous page, and that coefficient or multiplier of 4 is just going to stay out front anyway. It's like you're multiplying the function, so therefore you're multiplying its derivative. It's just going to stay with the term as you go through the derivative process. We then have to subtract theta, which is essentially like subtracting x. So if you were to use the power rule on this variable, you'd be left with 1. So let's go ahead and find our point and slope so that we can write our equation. Now we're looking at pi over 2. So unit circle time. Pi over 2 is the very top point on the unit circle. So sine of pi over 2 is 1 times 4 is 4, and then we have to subtract pi over 2. So it looks like our point value is 4 minus pi over 2. You could get a common denominator and simplify if you'd like to, but you can leave it like that as well. Let's check out our slope. So cosine of pi over 2 is 0, times 4 is still 0, minus 1 is -1. So now that we know the point and the slope, we can write our equation. We need y minus the point. Now notice how if you leave it like this, the point has two terms, so you should technically be subtracting both terms. Okay, show that concept by putting it in parentheses. So y minus the point equals the slope times x minus the tangent location. Okay, that pi over 2. Let's go ahead and check out G, which would be another trig one. Again, if you don't like the thetas in there, you can think of them as x's. So G prime, our derivative, power rule on 2 theta or 2x if you prefer that thinking, would just be 2. And then moving on to the trig, the derivative of cosine is negative sine, and we have that multiplier of 3 out front. So this would be negative 3 sine. Let's go ahead and check out the point and the slope to help us write the equation. So tangent location is pi, which on our unit circle is the leftmost point. So we're going to have 2 pi plus 3 times cosine of pi. So cosine of pi is negative 1 times 3 would be negative 3. We'll use our derivative to find our slope value. Sine of pi is 0, so negative 3 times 0 is still 0. Looks like we're just left with 2. Writing our equation, we need y minus the point. Notice how the point has 2 terms, so we need to subtract both of those, equals our slope times x minus the tangent location. All right, taking a look at our last one, no trig in this one, but it's not exactly in polynomial form just yet, so we will have to rewrite it to help us use our power rule. Notice how we have a root in the denominator, so we can rewrite that x as to the power of 3 over 2, and we can combine these powers on the x's. So when you are dividing x's, you subtract the powers. So 1 minus 3 halves would be negative a half. So notice how we can simplify the original function to this polynomial form, which is going to help us find the derivative. So let's go ahead and figure out h prime. So power rule, we can bring down the power, which would be negative 1. And then if we subtract 1 from the power, we'll get negative 3 over 2. We can rewrite that since it has a negative exponent. We can move that to the bottom to make it positive, and we'll still have a negative 1 coefficient up top. Now you can rewrite this as a root if you would prefer to do so, or you can leave it as that exponent of 3 over 2. Let's go ahead and try to find the point and the slope at the tangent location of 2. So plugging in 2 into the original, we'll have 4 over, let's see, 2 cubed is 8, and the square root of 8, I have no idea, so I'll just leave it like that. And then let's do the derivative. So plugging in 2 down here, 2 cubed is 8, and then notice how the division of 2 is representing a square root, so this would be the square root of 8 on the bottom. All right, it looks a little complicated, but there's still point values and slope values nonetheless, so let's go ahead and use them to write our tangent line equation. Y minus the point equals our slope times x minus the tangent location.